audiences to the benefit of both of those groups. So we've been doing this on a bi-weekly basis. We're skipping 2 weeks from now, but a month from now we will have another talk that's on
privacy in the information age. It's Fred Cade, actually, who's well known. He's testified in front of Congress and things like that. He's a pretty major figure on the subject, so we're lucky to have him speak. So in a month, definitely try to note that on your calendar.
Yeah, and for those of you who are interested, we can pass around a piece of paper if you want to get put on our mailing list. We'll just send out one reminder for each talk before the talk happens, so hopefully it won't fill your inbox too much. But today's talk is on brain-machine interfaces, and especially different kinds of eye tracking technologies and how to connect that with EEG and other brain information. And our speaker is Francisco Parada, who's from the IU Department of Psychology and Brain Sciences. So let's welcome Francisco.
Thank you for coming, and thank you for inviting me. So, first of all, some clarification. So, I don't particularly work in the field of brain-machine interface. So basically, it's not that I'm building these things or anything like that. So I do basic research in cognitive neuroscience, and the things that I do, as you will see in the talk further, they connect somehow with this goal for looking for means to actually make this science fiction topic come reality. So, oh yeah, thank you. So basically, this is a video. So if you can actually like, yeah, you might remember this. Let's see if the volume's okay. I don't know if you're old enough to remember this stuff, but we have the technology we can rebuild it. This is the opening. Do you remember this? Yeah, it's a bionic pen. It's a $6 million pen. So let's just forward. The one that doesn't remember, that's it, or the one that doesn't know, is a $6 million man, or the bionic man, how they used to call him. And in that TV show, they actually say, we have the technologies about this astronaut that suffered this accident and he's basically almost dead, and they say, we have the technology, we can rebuild him. And they rebuild him, and he's a cybernetic man with superpowers almost. He can run faster, he can lift things, he has super strength and stuff like that. Hopefully we don't have the technology, we won't be just like Peter Griffin, I don't know if you saw that. But basically, we're not quite there yet to make the bionic man. So hopefully we won't end up with Peter Griffin like that. But in this talk I'm going to tell you what is a brain-machine interface, what is the actual thing that we're going to be talking about. So I'm going to define it. And then I'm going to link it to some methods and signals, because at the end, all this stuff is more than the conceptual things. It's more about these super technical things, which is which methods we're going to be using to actually generate these brain-machine interfaces, and which measures we're going to be using, which signals. So, and finally I'm going to, and this is the punchline basically, the concept of neuroprocesses, which is like, is basically just like this. Think of a pirate or something like that has like this wooden leg or something like that, but this thing connects directly to your brain. Basically, that's the concept. And that's nowadays becoming something that is a little bit less, is getting out of the science fiction realm, in becoming a little bit in reality. So if we just go ahead and talk about what is brain-machine interface, one more please. And that would be, go back. It's a device that can effectively translate the intention to move or control into the actual movement of a robotic device or control of a software application. So basically, if you can get your body or your mind to move or control something that is outside with the use of some scientific tool or some sort of like robotic tool, that would be a brain-machine interface. So this, can you give once more? Basically, why would you want this? The main goal, and probably the way that everybody gets their money whenever they're doing this stuff, is because paralyzed patients will benefit tremendously out of this sort of technology. So they will be able to maybe move, maybe reach things, control computers and stuff like that. That's the main goal. And of course, bypassing these injuries, maybe some people that didn't have some sort of like some different injuries that might have paralyzed them. You can actually restore these lifeless limbs, you know. So moreover, just only controlling cursors and stuff like that, maybe you can actually have a new leg, have a new arm, and little by little become the bionic man. And of course, and this is a video also passing on, you can get the public, if you luckily you will stay healthy, you will get stuff like the mind flex, that you could actually like have a lot of fun moving this little ball around and passing it through circles. Just go forward. And so basically that's the concept of a brain machine.
What was that?
So that's the, can you repeat the video? Yeah. So it's this
What
little
is it?
gadget that is called the Mind Flex, and I'm going to go a little bit further. So basically it's this, play the video. It's basically this little device that connects to your head, non-invasively. So basically you can give it to children. There you go. And you can actually move, and that video is hilarious, that's why I actually... So basically it's like these little electrodes that are going to be collecting, at that level, in the Mind Flex, it's actually collecting only muscle movement. It's not coming from the brain, because it's only connected to your eyebrow, so basically it's mostly like eyebrow.
Okay, that's what I wanted to know. It didn't look,
Yes.
it didn't look at all reasonable.
So, but that was like, I don't know, 10 years ago, probably, or like 8 years ago, maybe. And I think it was fairly successful as a toy, because it's kind of like amusing to actually move this little ball around. But the common user will actually get that. The only way we will get to know that is through toys. So let's go into like more of the meat of this stuff. So basically, now that you know that a brain-machine interface will allow you to interact with a robotic arm, or maybe with a computer, without any interaction with hitting keys or mouse and stuff like that, we're going to be talking about the methods and signals. So first of all, the eye tracker. Why the eye tracker? Because the eye tracker has a lot of good things on it. But before I explain, I'm going to get you informed on what eye tracking is. So basically, if you have an eye, you can measure it, potentially. If you don't know, then you have the pupil, and keep going, and then we will have the iris, and then finally we'll have the sclera. And that's the three things that are going to be important for eye tracking, because we're going to be collecting information from this eye. So if you hit one more, you can see there are participants wearing the typical eye tracker, which is basically one camera pointing to the world and one camera pointing to the eye, and everything's being recorded by a computer. There are some a little bit like heavier weight eye trackers. So for example, this guy, which is what I have here. Can you go back? Yes, thank you. So basically, this is made by Dr. Tom Busey in psychology. It might look a little bit bulky, but the good thing about it is that it's all self-contained and costs less than $300. Well, right now I would say less than $400, because you need to do all the soldering part, and let's assume that you're going to pay for that soldering. But still, it's pretty cheap. And it's self-contained, includes these two cameras, these two monitors, where you can monitor what's going on. And as you can see, it sits on your head, and it's not that terrible. So basically, what you get out of it is an image of an eye. And the eye, remember, we have the pupil, we have the iris, and we have the sclera. And why is it important to know? Because these guys, we're going to be sending this light into it, and now we can actually see the infrared light. I'm going to skip some of the details. If you want the details, just raise your hand and say, like, I want that detail. But for now, and I'll happily explain to you. But now, basically, we send this light, it's an infrared light, to illuminate the eye. Since it's infrared, you can't see it. So it's not like you're looking directly to this light bulb. You won't see it. And moreover, actually, the photons that this infrared light is sending, they're going to hit the bottom of your eye, the back of your eye, and they're going to come back out because there's no receptors that will catch them. That's why you don't see them. So, but the camera, since the camera has more powerful optics than we do, is going to catch it. It is going to be making that bright spot of white light, which we call the first corneal reflection. And basically what it is that bright spot. But the cool thing about that spot is that it will give you a sense where the back of your eye is, basically. It's like a ground truth. So, as you can imagine, the eye in this movie will move around. And this little white light will remain fairly constant. Will move around a little bit, but it is always going to be dependent of the pupil. So basically, then mathematically, it's super easy to actually get to know where you're looking, because you can catch these two circles, as you can see them here, in the green and red. Hopefully you see them. And you can easily see the center of them, catch the center of them, and then draw a little line between these two. And then you have this value of this vector, which is the length of that line. And that will be a marker, a unique marker per each position of your eye. And then, and I'm saying like it's mathematically trivial because basically all those algorithms exist and you can Google it and see it. And if you click next, that's the other thing you get. Don't push the movie yet. So basically, the other thing you get is the movie of the world. So because we had a camera pointing to your eye and a camera pointing to the world. So basically, up there you can see the eye, and this is what this person was looking at. And now that we know a value for each one of the eye positions, we can make a calibration. And then if the movie starts, we told this person, okay, every time there's a little light, you can see it there, it's going to turn on. Look at it and stare at it for a little bit. So now we know the value of where the person is looking at each one of these times. So we have a value for that, we have a value for that, and now it's just a matter of interpolation, which is a common and fairly widely used mathematical procedure to actually start knowing the value, the potential value of each one of these points which we're not calibrated to. And then we can get these movies with these crosshairs where it indicates, the center of it indicates where this person is looking at. So if you push next, basically what we have is, if you put all this together, we have this person that just finished an experiment. It was interacting with this computer. And here's the eye. And if you send the movie, oh, you have to click the movie. There you go. You can see in that little red dot, hopefully you see it, where this person was looking at. So he finishes the experiment and joins the conversation. And as you can see, this person is interested in the conversation and looks at the mouth and faces of people, and you can see all the stuff that he is actually looking at. So basically, what you get is an eye tracker, and don't start this movie. So basically, can you go back? Yes. Hopefully you got what the concept of eye tracking is. So basically, we can actually see where this person is looking at by. When I'm saying like fairly simple computations, is because everything is open source. You don't have to reinvent the wheel, basically. So once you get that, the possibilities of generating a brain-computer interface are right there, and you just need to go and get it. So basically, if you go forward one, this is the Tovi, is a company that actually makes these eye trackers, and they developed this system which you carry around. And I hope that I mean, I suppose that if you're paralyzed, you won't carry this around. Someone will do it for you, and they can just mounts easily like that with a magnet thing. You just connected it with this like USB cables and micro USB cables to the power, and there's another in the computer here. The second computer is going to be performing these computations that I explained, and basically you will be able to calibrate. They don't show the calibration very much because it's the tedious part, but they assume that the calibration is the simple thing, and then eventually what they will be able to do is that he can click anywhere that he wants, and then he can move items around only with his gaze. Where he's looking at, he will just grab the thing, move it around. He can click open software like Microsoft Word or whatever. They have their own proprietary software, which is the one you see here. The person just calibrated. It's the same principle. These little dots on a screen, and then here the person is calibrating the whole system, and you can see how he is not using his hands at all. He's only using his gaze. So, and he can also type. As you can see, he could potentially open Microsoft Word. Yes, please.
What does that mean? How do we actually?
Good question. So basically, if you know where he's looking at, you can measure it, and you can. It's a matter of just setting a threshold. So basically you could say there are some, it all depends on the user. So here's where you get in the murky terrains, because this looks fantastic, you know. The guy's there, you know, flawlessly driving this thing, but the problem is like, huge problem, like how do you actually make the click? It depends on what kind of like, if you're a tetraplegic or something like that, it depends on what are your abilities. So if you're capable of actually holding your gaze for a little bit, let's say 30 seconds, that can be the way to see the computer that you want that item. So basically, if I stare at this thing for 30 seconds, click. What if you have some sort of like tremors or something like that, tremors, when you have, because some people actually can't get their gaze focused. Sometimes, but they can verbalize stuff. They can verbalize. So sometimes you just put a microphone and they just like do something like and it will just click in the place where they were looking at, and whenever they actually mention the word. So it's all a matter of fine-tuning a threshold that you might find for the particular patient.
It looked like the psychotic random motions seemed much smaller than I remember them in other things.
So basically, it's so smooth because you get this time series basically of all these values where the gaze is looking at. So basically, what he's asking is that he remembers the eye tracking being a lot noisier, basically, that the thing just wiggles more than it did there. You can always tell the computer to say, make an average with the 5 last points that happen, and then everything gets a little bit smoother. So they do these averaging windows in order to make it smoother. And also the calibration that they use is, I would say, fairly good. So it all depends on calibration. Yeah.
What is the average price for this commercial system?
Good question. So basically this guy, this very same guy, is as cheap as $6,000 and $900. Is that how you say? So $6,900 basically. So it's cheap, but not really. So yes.
Has there been a movement, like for the insurance companies, to convince them to cover this cost for paraplegic and quadriplegic?
That's a really good question. As far as I know, they don't. The insurance doesn't insure anything. So basically, it costs $6,900, and you might say, wow, but that immediately cuts all the possibilities of my aunt, of my grandma, or whatever, my neighbor, to use it. Well, the thing, and here it is. So these technologies are fairly new. The whole concept of eye tracking has been, the first eye tracker was like 1896 was the first paper. Might be off for 2 or 3 years, but it's like late, like 1890s, basically. During that decade, it came. Of course, as you might imagine, it wasn't using these cameras. It was using like these pictures that you would take every, I don't know, couple of seconds, and you could like actually see where the person was looking at. But now that things are improving in terms of like technology is getting cheaper and cheaper. Actually, let's go to the next video. And this wasn't prepared, by the way. Did you hear that? So basically, these guys take the same principle that we do with our system, and they buy off-the-shelf equipment, cameras. Basically, you can buy an 8K camera for like I don't know, less than 200 or so bucks. They do that. They just mount it to some glasses and put the LED, as you can see, the infrared LEDs, and can actually connect it to this person that is paralyzed. And they have the little computer, because the software, as I'm telling you, as long as you actually know how to do this stuff, you could just solve it. It's a matter of like copy-pasting some code and just like typing something else, and he can actually control. So this guy is a graffiti artist that has a neurodegenerative disease, so basically he's getting paralyzed, and eventually he will die when his brain will just stop making him breathe. Probably they are going to keep him connected and breathing for a little bit, but then after that, once the heart stops working. And as you can see, the algorithm basically is tracing not the location, but the actual trajectory of the eye, because this eye tracker was made for him especially so he can continue doing graffiti. So basically, once you have the heuristic of like, okay, I know where this person is looking at, you could just set the threshold. Is the person going to stare at this thing, and I'm going to click it? He's going to verbalize something, he's going to click, or I'm going to follow the trajectory so he can write. And of course, you can actually go, once you have the concept, and you can go even cheaper and even simpler. So actually go for the next video, and you can see the case of this guy. I think his name is George, and he got paralyzed in a car accident. So buckle up. This is the whatever. Well, anyway, so this person is studying now, and if you can see that, he wears this little red thing in his head, and has these little 3 bones, as you can see. Maybe whenever they are going to show it again, there it has 3 little balls there that are reflected. Basically, these are like highly reflective spheres. And they, and you go back, and basically what they do, the system is pretty simple. They have this computer screen. They shine this infrared light into his face. These spheres will actually reflect it, because they are highly reflective, so they will reflect it. You see, that's the thing that actually shines the light, and it collects there. And you might say like, wow, this seems like things from the future. No, just grab a Nintendo Wii and you have exactly the same technology. That's what they do. They have like this infrared cursor that you just like go like this, and the little avatar or whatever, Mario Bros or whatever, he will move its arm anyway. So this guy actually moves his head, and these 3 spheres will actually encapsulate, in a way, the thing he wants to click on. And whenever he actually marks it in the screen, he just verbalizes and says like click, and the thing clicks. So the technology can go even cheaper. Once you get the concept, and once you get the software, you can get even cheaper. So let's go forward. Do you have any questions or any comments or anything? Good. So, of course, why everybody doesn't use this? Why the whole thing of like people being paralyzed is over, and we don't have any more of this trouble? Because there's a lot of and triggers another thing. So if you click, you say, I want to take a bite of it, because that's a cognitive process that's going on. And then the action that cognitive process triggers is you bite and chew. And probably this output is going to be deliciousness. It's going to be, this is fantastic. So then, this output actually will trigger again. I want more pie. And it's a thing that comes and goes. So if you click, the big problem is that usually all animals, all like humans and all other species, we just engage in this like sensomotory loops. You're not there and you just don't like flash this face or like this pie and you say like eat and the process ends there. You're in this loop and that makes a big problem to get out of the screen of these like computer brain machine interfaces, because you're always encapsulated in that virtual world. So if you click, we have three problems: a what, a where, and a how. I'm going to explain you through a little bit of the what. So click again, EEG or ECOG or whatever. This signal, this electrophysiological signal, is ugly and messy, and you can see it is this line that doesn't mean anything. It looks like a 3-year-old just like drawing. But you can actually decompose it and get more structure out of this. So basically these complicated lines that we get, these complicated signals that we get from the brain, you can actually decompose it using several mathematical methods. There's no need for us to go there. But basically, you can transform this guy, this very noisy and senseless guy, into this collection of more organized and more understandable signals. So the question is, if you click once more, you could say, okay, I'm going to measure power. How much of this guy, the guy that was slow there, for example here, blue means that there's very little, red means that there's a lot. Can I actually be measuring this stuff? And every time this slow guy that was there, that I got from the brain, increases in power, it means that I can click. Fantastic idea, actually we could do that. If you click again, maybe we could say, what if I have my EEG cap and I can measure the global organization of what's going on between electrodes? It doesn't matter if that represents some sort of cognitive process or whatever, but I could actually do it. What if I could actually say, I'm going to grab features? So for example, the one up there, there's clearly like a line here, there's clearly another line here, there's nothing. What if I grab one of these features and trigger my machines? That's a fantastic idea. The problem is that computationally we are not there yet. We collect the signals, we kind of know what they mean in this very particular and limited context, like the phase that comes here, the phase that goes out. But we need a deeper understanding of what the measures and what the signals mean in order to actually say, okay, this person is actually computing, or the brain is actually computing for the piece of pie. And then the next one is going to be computing for the reaching. So, as you can see how this works, hopefully, I know that might have been a lot of information, but the main point is that we can get all these signals from the brain, but up until we know what they mean, we won't be able to use them completely. We can definitely use them if we set up our own rules in this virtual world. So this little gadget is called the EMOC or something, I have no idea how it's called. The emotive is called. So basically it's an EEG with dry electrodes, because the things they're getting cheaper and cheaper, as I'm telling you. So basically you can get these, I think it's like for $500 commercially, and basically it's a headset. Put it there, you know, like look like you're coming from the future or something like that. And these guys will measure electrical activity. And it really doesn't matter. It really doesn't matter what is coming. It's measuring from the brain? We don't know. It's measuring only like muscle movement? Probably. But it really doesn't matter, because this is a movie. This guy is wearing the same thing, the emotive. And basically, there he is calibrating. So basically they're saying, okay, think that you're bringing back and forth this little square. Now think that you are actually putting it, like holding it in the middle. Think that you're moving it to the left, to the right. And as he does that, the computer gets the signal, the whatever signal it is, and is going to map it to that. So every time that feature appears, the computer knows that the person is actually indicating left. And then now he can actually go into this virtual reality world and move this little robot around. It's very like clumsy, as you can see. You know, the guy here is like making all his efforts, and the robot is kind of like moving. There he's moving, yeah, but it's still like clumsy. It works, but it's fine. So basically, Emotive is an application for gaming, pretty much. Leave it there. There's a movie there, but not yet. It's an application for gaming. So basically, it's the first video that I showed you with the little ball, 2.0 basically, in the sense that now I can have this complete reality sets where there's someone walking and complete tasks and stuff like that. Yes, please.
So with that, when it calibrated it, is that calibration permanent, or is it using like updating some like machine learning algorithms to change it and get smoother over time?
Super good question. Sadly, this system does not do that. So basically, the calibration is fixed for that one session. So then you can see the problem immediately, that every time if you have a patient that is going to be using that, you don't want that. You want it to be learning, you want it to be doing this thing. And that's a computational problem. So basically, we need better algorithms that are actually going to be able to be learning faster. And also it's because we don't know the signals yet. We don't know everything about the signals. We don't know what theta, like oscillating at 4 or 8 hertz or whatever, is going to be doing every time I speak, you know? We don't know what this high frequency guy is doing. You know, all that information is missing. There's a lot of people working on that, but there is that translational part that's still missing in order to train the algorithm very well. But that is because this guy is not invasive and you're getting a mixture of things. So if you actually roll the next video, you can see someone, controlling this hand, just like Luke Skywalker in the movie Star Wars. And it's the guy with the the microelectrode implant in his head. He thinks about doing this movement, and the bionic hand, which is just a little robot, actually does it. It's very clumsy still. The thing is right there, but it's happening. It's yes, Alex.
Yeah, so I mean, is he actually thinking about that movement, or has he learned to make some kind of thought series that is then the algorithm figures out to interpret that as meaning?
So that's a really good question in the sense that the instruction that they gave him was to think of this. So basically the golden thing that we are looking for basically is that if I can actually think of doing this, I can have a signature of that in the brain. I can have a fingerprint of that in the brain. Please.
What part of the brain is that directly connected to, and how does that...
Super good question. So why did they start there? So you said like, well, they could have implanted the electrodes here, whatever. The motor cortex is super well known, it's super well mapped, because basically our motor cortex is exactly or very, very similar like the monkey motor cortex. So basically that motor cortex has been mapped very well, and it almost mapped one-to-one to the human. So basically what we learned there, we could apply it very well. So basically we know exactly where the hand area is in a way. So basically that's why they implanted it in the motor cortex. Would that be as easy in the, I don't know, like sensory motor integration? Whenever I say like, grab something and say like, ooh, it's cold, I'm going to drink it. Definitely not. That is super like obscure and we don't know yet. But these simple things of like, for example, twitching your finger, it can be done in the psychology department. We have a TMS, which is a transcranial magnetic stimulation machine, which basically what sends is imagine this like device that shoots this electromagnetic field into the brain and activates something. We do all that all the time of like, look, I'm moving my hand with this machine. So basically, it's because we know the motor cortex. That's why they did that. And that's why they asked him actually to do this. The question is like, is he actually doing that? Or he's compensating, he's accommodating? Because this doesn't work. This is the trial that worked. It's not that it happens all the time. Yes.
Yeah, but cognitively, we do things like this all the time. You drive a car, you're not turning the wheels. You're performing an action that generates a result. And so as soon as you learn to drive a car or ride a bicycle, you short circuit the question of whether you're thinking about the hand. You're simply thinking about having a result, and then your brain takes over. So you don't need to think about the hand. It all translates.
That's a great comment. That's a great comment. The shortcut that they tried with this guy was, okay, let's try to do this one-to-one mapping, because it would be so elegant and so nice if actually we could do a one-to-one mapping from electrical activity to function. But actually, I think that the next slide maybe the where thing, and I'm going to come back whenever we talk about how. I'm going to come back to what you just said. So then there is this other question. Think about the loop. Usually I don't just go and say like, okay, I'm moving, and this is exactly what you're saying. I'm not turning the wheels. I have this whole concept of this machine that I do this and the car does that, and I'm controlling the physics of like how much I have to turn, and I have all this experience, all this thing happening. So there are all these loops inside loops going on of activity in the brain, super complicated. And then the question is like, okay, maybe if we actually want to take all these people from being controlling a little mouse cursor in the screen, and we actually want to take them out in the real world, we need to close the loop. The brain receives things every time. So think of the example of the pie or the water. And if I say, I just go there, grab it, feel that it's cold or whatever, and that makes me think that I really want to drink that water. And then I drink it, and then you trigger these other things that are going to be looping around. So basically, the brain constantly is receiving feedback from the world. It's not just there, commanding things. It's constantly there. So that's another bigger problem, because we say, okay, we're kind of dizzy and confused, adrift, I don't know, dumbfounded, whatever you want to say, in terms of like, what does it mean whenever this signal appears in our measurement? But then the question is like, wait, what if I want to tell the brain that this thing it needs to be grabbed or needs to be drunk, So you need to close the loop where the brain actually receives something. And here's where the whole brain-machine interface thing just falls down if you're only living in a virtual reality. So basically, there are several things. So this is a super schematic representation of how the brain is connected. So basically you have the spinal cord, and you have different nerves innervating limbs, and then you have the thalamus, and then you have the cortex. All these things are like massively connected to each other. And the question is like, okay, if I want to inform the brain that this water is cold and is good to be drank or whatever, or is the pressure that I'm actually exerting is good enough so I can actually grasp, where do I inform the brain? Do I do it in the limb, here at the nerve level, and then it will go over there? Do I do it here in the spinal cord and go to the thalamus? Do I do it to the thalamus directly so the thalamus can send it over to all the other cortices? Do I do it in the cortex? Complicated, so many levels, and every time I move to the left, to the nerve, to the spinal cord, and to the spinal cord, to the thalamus, and from the thalamus to the cortex, the complexity just increases exponentially. So the question is like, where do I inform them? If the person are paralyzed, so it would be easier to say like, let's start here in the easier level, nerve and spinal cord. Usually when they are paralyzed, they have their spinal cord severed. So basically, you can't actually talk to the spinal cord without being able to send information over there. So probably it will have to be in the thalamus, super deep in the brain. It might not happen. Do it in the cortex, the most complicated structure. The level of complexity that is going on there is super complicated. So this is kind of disconcerting in a way, the where. But then there's another problem. There's even another problem. Let's go further into the how. How do I actually tell this to the brain? How actually do I, if I actually say, okay, it's the cortex. Let's say, how do I tell it? Because I have to send a signal, which is not going to be the native signal that the brain sends. So basically, one option is to use the native signal. And this implies that I understand the what that I talked at the beginning. So here I'm going to just like mention some things. If you want the details, I can also tell it to you. But there are several coding things happening in the brain. There are several ways that the brain talks to one part to the other. Some people call it like the temporal coding, which is basically every time a neuron fires, that particular time is going to be important to consider all the other trains of spikes, all the other firing that happens. Maybe it is like that, click it. So basically an emphasis on individual spike. So I can actually measure what neuron is saying. The rate coding, which is emphasis in the correlated firing rate. So basically if I have it considers that the brain just fires randomly. So basically, what if I correlate this guy to this guy? Every time that this guy happens, this other guy happens, that means something. I could use that. Can I use transient coding? So basically I go up a level and say I'm going to do an emphasis on the correlations of these dynamics that are going to be happening in space and time in the brain. Super complicated. Do I know what that is? There's a lot of people working in all these three. And there's a fourth one actually, synchrony. So it happens that maybe this neural population get in synchrony, just like I don't know what gets in synchrony, like pendulums on a clock, for example. They will get synchronized. Will those synchronizations will tell me about the functionality of that event, and I can use that and then send this over to the brain in particular frequencies and particular amplitudes. Complicated. We don't know. There's a lot of people working on all this stuff, myself included, on trying to like figure out what these things mean, how we can actually understand the signals, what is synchrony doing, what is transient coding doing, what is rate coding doing, what is time, what is space doing in the brain, basically. So that's one option, it's overwhelming. The other option would be like use a brain-friendly artificial signal. What do I mean by this? Think of cochlear implants. When cochlear implants started in the 70s, I'm pretty sure that a lot of people said like that's not going to work. The signal you're sending is too like far. But the good thing is that cochlear implants, although you have to have a set of requirements to be implanted, and there's a period where you only hear noise, the brain, the signals that this cochlear implant is sending to the auditory cortex are friendly enough to the brain. So the brain actually at the beginning is like, what's this? I have no idea. So then the people only hear like certain noise. And then after a while, things are starting getting like accommodating and the brain starts like discriminating. And nowadays people actually, the technology is so good that people can actually enjoy music sometimes. So, and as well as conversation. So maybe a brain-friendly artificial signal might be the thing that we want. But in order to do that, we also need to know all this loop thing. We also need to know where to close the loop and how to actually input these guys. As you might be thinking, okay, all this like simulation going in and out will have to be invasive. Probably. Although with these electrodes coming cheaper and cheaper and smaller and smaller and better, maybe it will be something like we can set up an electrode that is measuring and next to it an electrode that is actually sending signals. Who knows? Now we're just jumping fully into like science fiction. So, but it might be the case that we might want to actually understand the signals and simplify it. Maybe the brain is smart enough. Actually, the brain, the most awesome thing that does is that accommodates to everything. It learns so much. So maybe once I understand the signal, I can simplify it and send it over. So now let's go and do the punchline, the neural processes. So basically, once these three problems, what to measure, where to actually measure it and where to send it back, and then how to actually send it back, how to talk to the brain back so this person can actually move again. Before it gets solved, after it gets solved, we're going to be able to go and do stuff like this. This is a monkey which has a motor cortex, and I'm telling you, monkey rhesus has really, really similar motor cortex as humans. And he is actually controlling this robotic arm with the intentionality of grasp. And this computer is translating where the arm goes and where to grasp it. You can see anything from a marshmallow. He's having some trouble there, but he can actually make it. So, and this is terrible because in a way it's good and bad in a way, because these advancements, they are all come from two things that are really, really bad in science: profit and animal research, or things that society kind of like says like, ooh, you know, you're profiting with science and you're doing animal testing, liberate these monkeys. And it's terrible, I know. I can't say anything there. There's a lot of ethic, and that will be like another talk. But they are helping us to actually figure out what signals, and creating algorithms that are going to be learning these signals, what the signals mean, and how to actually control this in 3D. And to finish, basically, I want to show this. This was published like a couple of months ago. There's no need to actually know the audio. Basically, this woman has exactly the same implant that the monkey had 2 years ago, and she actually is capable of grabbing this arm and not controlling it only in 2D, but also in 3D, and she is capable of drinking water, as you can see there, and she gets really, really happy when she realizes that she can actually move that arm, drink water, and she made it. So, and then she can actually, the other part is like, that's 50%. Now she has to return it back into its position and doesn't have to fall. And there we go. She's like super, super happy. So, little by little, these things that are like, kind of like, they were kind of science fiction, they're turning into reality. 5-7 years ago, the only thing that people could do was moving cursors in 2D screens blocked in this virtual environment. This paper was published in May 2012, so just a couple of months ago. There are two patients, it's her and a guy, the guy that you saw before. And this task, I think that she could only perform at 45% of the time. So as you can see, there's all this translational problem. There's still all this translational problem, and it's only because we don't have a very good understanding on the signals. So, and basically, I guess that my punchline, finishing line, take-home message is that there's a lot of like complexity going on in the brain. All this complexity can be deciphered. It's not that we're just not going to do it. I mean, this was unthinkable 10 years ago. The signals are getting decoded. Computer scientists are improving computational time. So basically, instead of like taking a month, in 2-5 more years, this is going to take like, I don't know, a couple of hours, hopefully, in compute, and to do all the math. Little by little, once we understand that, we can start moving back in the invasiveness. So therefore, we won't have to actually drill a hole in this patient's head, and maybe we are going to be able to use this not only to play around with little games, but also to control devices in the real world, and eventually probably have like bionic arms and stuff like that, just like in science fiction. Well, thank you, and hopefully there will be like some sort of like questions or discussion. Thank you for listening to me. Any questions, comments?
So I have a question. It's really about the eye tracking, because it seems there was this video of the guy, first off, looking at the room with the women. And you will learn a lot about the person whose gaze you're following. So I wonder if that isn't very appealing to advertisers, for instance. Is there any kind of movement to take advantage of eye tracking to figure out what people are looking at?
Oh, that's a huge research field, and it's the main commercial application of eye tracking, actually. So eye trackers have becoming so popular and cheaper in a way, because you can use it for marketing. You can use it for like business, or like designing websites, see where people are interested, designing books, for example. So it all depends on, and that's a reason, let me go back. That's a reason why eye trackers are getting so cheap and at the same time so expensive. Because they're getting cheap because now they are like getting into the public. So now a marketing company will be able to actually buy, or they want to buy an eye tracker. But they don't want a scientist or a team of people controlling this machine. They want it to be simple and easy. And that's a computational part that you have to hire these hundreds of engineers or computer scientists to actually program a software that is going to be simple enough. So my subject will come, sit down, put the eye tracker, calibrate it as quick as possible, as accurate as possible, and go to the world and keep that calibration for as long as possible. But, and they are making it. Tobii, they are like fantastic in this sense. You sit down, they can do it with babies. All the research that is being done in the psychology building with babies. The babies come, they're all fussy. Think of this, the worst baby ever. They usually behave like that because it's like new environment, weird people, you know, all this equipment. They just get super fuzzy or whatever, and the equipment is capable of actually calibrating, getting data. Of course, the people, the scientists that are working there, they're like super prof. They calm down everything. They take control under it. But Tobii or ASL or all the other companies, they do a fantastic job in this stuff. And yeah, people can definitely, now the newest thing is like going wireless. So this is the open source version of it. Of course, it weighs a little bit, it looks bulky, but you could potentially, the commercial versions of that basically doesn't have the electronics exposed. It's the same thing. Weight's pretty much the same and just costs like $7,000 more than this one. But yes, I mean, applications of eye tracker can be anywhere. And I guess that now computers, there are people doing some Windows 8 patches. So you could use your webcam in your tablets or your new laptop with Windows 8 and you could be able to actually like click with your eyes. I don't know how much of that will fly since like now is everything like kind of touch, you just like have all these like touch sensitive screens. So I don't know how much that will fly, that idea. But I know of developers that want to use the webcam, the front-facing camera in order to track your eye. Yeah, so there's a lot of applications in the real world outside the brain-machine interface for eye tracking. Yes. Natasha, please.
I was wondering how much collaboration actually happens like between researchers, because I know here on campus, Ray Berg in business school, he actually works with commercial companies, and they have this really nifty thing which looks just like regular glasses. It costs $40,000, but it has the forward-facing camera. You can track both eyes. I mean, do like you guys work with that laboratory together, where you sort of rent out equipment in exchange for something like barter kind of trading, or is there no collaboration whatsoever between cognitive research and business school?
Even though the cognitive science or psychological and brain science department is like super like global in the sense of that everybody talks to everybody, there's so many, I just can't talk in the name of the researchers. So basically, I'm not particularly interested in going out in the world. My scientific questions don't get answered if I just put eye trackers in everybody and just like send them out and do things. But social psychologists, they might definitely be interested. I have no idea if they are actually working. I know that Elliot Smith uses a lot of virtual reality. For example, there are people, actually, Alejandra is sitting there, she collaborates with us in generating this thing for dogs. So they can actually learn where the dogs are like performing all these tasks. So that's a collaboration, for example, from cognitive science or the the animal behavior group with people more in the cognitive or cognitive neuroscience areas. Definitely there might be room for more, I guess.
I was in Cambridge recently, and I had a chance to talk to Stephen Hawking's tech guy. And so Hawking, as you may know, uses this mainly to write, both to write speeches and to write books. And he lost the use of his hand recently. He had been using his hand sort of like a Ouija board to pick out letters. And so they put a camera on his glasses that focused on the only muscle he has left, which is in his cheek, and he's been controlling his speaking, picking out letters on the Ouija board by simply moving his cheek up and down. And his tech guy said he was trying to get him to use an alpha wave thing to like control a mouse on his screen, and his tech guy could do it, but Hawking didn't like it, and so he's not using it. I didn't see anything about speech generation or about this thing, which I think Hawking's tech guy is trying to use. It's like alpha wave control just for the mouse, just to pick out letters on the screen. Yeah,
So in terms of like, so the case of Hawking is that he actually like selects. It's just basically the same thing.
Words, phrases, and
Yes.
letters. Yeah.
With speech, there were some tryouts of using this alpha wave, which is it's a slow signal. Remember when this EEG blue line that was pretty noisy, you can split it into like more organized ones? There's one signal that actually oscillates, so wiggles in time between like 8 and 12 hertz, so 8 and 12 give wiggles per second basically. And that's called the alpha wave. And that's slow enough that you could actually, here there's alpha, you see, but you don't see it wiggle. But anyway, but it doesn't work really well. So basically they have been testing it, and the thing is that alpha won't be all the time related to the particular letter, for example. So that's a problem. Yes, please.
Is there any push to start to combine these technologies so that you said alpha wave doesn't work very well, just a percentage of the time, but maybe it would work enough combined with the eye tracking to where you can get a higher percentage success?
So that's a super good question. So actually I'm trying to publish a paper now with eye tracking and EEG combined. Basically that increases and puts another problem there, because it's kind of like the awful truth in a way of all these things, that there's a lot of noise in all these measures. So EEG, this guy for example, probably mostly works with all these like muscle movements and stuff like that. In the research EEG, we try to, these are enemies basically for us, all these like muscle movements, eye movements, because they are orders of magnitude larger than the signal that we can catch from the brain. So whenever you insert eye tracking there, you have these like waves of electrical activity, all washing out basically what the brain is actually sending. But now, like machine learning algorithms, someone mentioned machine learning algorithms. There are machine learning algorithms that are good enough that actually, since the eye movement and the blinks and all this stuff are so stereotypical in the electrical profile, you can actually make this algorithm learn it and then remove it. So basically, the options are there. I'm going to try to publish this guy. There's one more that was is another heuristic similar to the one that I'm trying to publish. Probably better, I must say, like better. No. That it was published already in like 3 or 2 months ago. So basically, it's just a matter of time. As I'm telling you, like it's a matter of time that we start like keep working and figuring out the signals and coming up with measures that are more robust, more sensitive. It will be interesting to actually combine EEG and eye tracker. The problem with that is that it's extremely painful because you have to have all these gadgets. When you put too much technology together, it tends to fail something. So it is kind of complicated when you actually put more and more equipment. So it will be awesome if we actually get a measure directly in the brain, non-invasively. So basically, I would say what I would say is that it would be fantastic if I can actually wear this emotive thing, just put it there, and have an algorithm that is smart enough, and I have the knowledge to actually say, okay, I'm thinking of the letter M, and that thing will appear, basically. But yeah, I mean, people are trying things, definitely. Thanks.
That multi-electric, the kind of three-dimensional array that you showed, that looked pretty solid. I mean, does that, if you sink that into brain tissue, does that damage some other part of the brain tissue?
So it doesn't. So the thing is that it's so dense that I think that damages some stuff, but then it will just like, if it damages, it is not, you don't notice basically. So basically so small that it can go, the main idea of it is that it goes in between cells. Of course some of them are going to get crushed, but I think that they are not like enough. I have never heard anyone telling me, so I don't work with monkeys, we can't work with monkeys here in IU in doing these arrays. And as far as I know, epileptic patients also don't get any sort of like research here because I don't think that we have that. But my friends that actually work with this stuff, they have never told me like, yeah, every time we implant it, 30% of the time, we just kill everything in there. No, I don't think so. The problem with the implants is that it's open and it's very propensile to infections. So that's why the good thing would be to actually go no invasive. Because that way you can use it, I can use it, the person that is paralyzed can use it, and no risk of infection. Yeah.
And we should probably wrap up pretty soon if I can ask one more question. So with current techniques, I mean, would it be possible to interpret, let's say if I tell a lie, is it possible to know that?
Good question, good question. So there was someone tried this in fMRI. They found some stuff, of course, wasn't robust enough. The signal, fMRI signal is not robust enough for these cases. It's too slow. Someone tried it with EEG, because EEG, the cool thing about EEG, I don't want to say all the good things about EEG because that's the method that I work with and I love it. So I don't want to say it, but the good thing is that it's small, it's cheap, and records millisecond precision, so basically super fast. People try it, and they try it with a component that is called the P300, which is this positive deflection that goes in this wiggling line that happens at 300 milliseconds after a stimulus onset. So basically, if I show you something, this positive deflection will happen 300 milliseconds after I show it to you. And it usually is stronger, it has more power whenever you see a target, something that you want. So that's a potential thing that you can actually explore to say that, oh, I want that glass of water. Boom, a B300. First of all, the measure is not robust in every trial, so you have to think about it several times. And second of all, it has to be an average, so it's kind of slow. But going back to your question, someone used this measure for people that were included in this crime, or they were suspicious of being in this crime. So let's say someone murdered someone with a knife, and the particular knife is like this cooking knife, whatever. You have the thing, and if you see this person that is innocent, and you just tell them like, okay, think about the night of the murder, and you start flashing. And actually, this is the actual paradigm that they used, and they start flashing objects: a glass, chair, spoon. The B300, since it's not associated with that night, won't be a target, theoretically. But the knife, since you use it to kill this person, it's a target because your brain knows it, you just use it, and now you're thinking about it. It's just like, don't think of an elephant right now, like you start thinking. So the same thing. Think of the night, what happened. We know that it was a knife that you potentially use, whatever. So they prime him, and when the knife appeared, the brain started doing a P3. Compared to some control subjects, the P3 was lower. The problem there, you could say like, wow, we just named it, we have it. The problem was that some subjects that the scientists knew that they weren't involved at all. They also showed some P300s that were robust enough. So it's kind of like scary. So they have tried, and the problem is back to the same. We don't have a full understanding of the signals, what they mean, what they're coding for.
So, taking what you're saying there, is there anything beyond that, a functional or computational barrier to like external brain control? Like if you had it all worked out well enough and you knew like brain state X, whatever the brain state was, whether it was when I'm thirsty with less of water or whatever, could you induce that brain state to someone through like
from like far away?
Well, I'm not sure how long they say true. So
So
let's just say like right on the skin, right? Like
yeah,
let's say this device that you put
So the question, let me see if I understand the question. So if we actually know what the signals are, if I say like, okay, if the brain wants to actually feel this cold glass of water, can I actually on purpose send it to you and do this? Well, okay, now we're jumping into like the science fiction. Yeah, it's super fun with mine. Don't cite me in this one. I would say, okay, it's super hard and it's difficult to actually like send a signal from far away. These signals don't travel from far away. So basically, there's no way I can actually control your mind. It won't be able. My magnetic signals and electrical signals won't be able to do it. Mainly because here's air, and if we were in water, I think it would be a little bit simpler. But we're not. And then the other thing is that it has to be like really, really close. So the closest thing to like sending signals to the brain, first of all, is like electrode implant there, send a voltage. The other one is DC direct current stimulation. So basically, you just put a patch, send some electricity, and activate the brain. The third one is TMS, which is the same thing. TMS is the transcranial magnetic stimulation, so you send a magnetic pulse. Everything has to be like super close to the skull and is fMRI guided, so basically you know exactly what the brain of these people look like. So you have a TMS, you have the brain of the person on the screen, and you have calibrated and map out, work for like 25 minutes in order to try to see every time that my TMS coil is here, is pointing to exactly this place in the brain. That takes a lot of work. And then you have to work it out and blast it away, and it doesn't work it works reliably, but you have to do like several testings. So it's kind of complicated. You will have to be wearing some sort of helmet connected to like this like big matrix of like conspiracy or something like that. But yeah, I would say no, but potentially if we actually figure out, yeah, why not? You know, but we're kind of far away from that.
Well, thank you.